I'm Himanshu Vasnani from Department of Mechanical Engineering. We are on a subject called Material Science, and subject code is ME207. Unit is 2, lecture number 2. Today's topic are fatigue failure, mechanism of fatigue failure, and effect of alloying elements. So, our objective of today's lecture is to provide students with a basic understanding of fatigue failure, mechanism of fatigue failure, effect of alloying elements, and the outcome of today's lecture are students will have learned the basics of fatigue failure, mechanism of fatigue failure, effect of following elements. Students have understood the various students will be able to understand the various parameters of fatigue failure. So we will start with the fatigue failure. See, what do you mean by fatigue? We have seen in our lab also various times we have seen some kind of fatigue failure happening. So I'll explain you like it is a failure of a material by fracture when subjected to a cyclic stress. So fatigue can occur at a stress whose amplitude is much smaller than the static load required to produce fracture. Okay, I define fatigue once again. It is a failure of a material by fracture when subjected to a cyclic stress. When the material is again and again applied to a repeated stress, then this happens. Then fatigue can occur at a stress whose amplitude is much smaller than the static load required to produce fracture. The maximum stress that a material can withstand without failure for a specific large number of cycles of stress is termed as its fatigue or endurance limit. Okay, the how much stress it can withstand without breakage, without failure. Okay, for a large number of cycles of stress is called as its limit, its fatigue limit, its endurance limit. So the fatigue is distinguished by three main features. First is the loss of strength, second is the loss of ductility, and third is increased uncertainty in strength and service life. Okay, so we need to understand limit. Okay. Then engineering materials are often subjected to fluctuating loads while in service. A few examples like uh, few examples of components which are subjected few examples of components which are subjected to fluctuating loads of or alternate stresses are like aircraft wings subjected to turbulent air, leaf springs to and fro, bend to and fro, then connecting rods pushed and pulled in piston engines, some sorts of compressors, pumps, turbines, etc. subject to repeated loading and vibrations. So these some components that are listed here, these are subjected to fluctuated loads. Okay, and they are made for such kind of loads. Okay, so uh, let's go further. Uh, if a metal wire is bent to and fro several times, it ultimately breaks. We have seen that in the earlier, if you take a metal wire, it is thrown to and fro bended, then automatically it breaks down. So rotating and vibrating parts of machines, as in aeroplanes, are liable to undergo fatigue and fall accidents. The all the four examples that have been discussed in the previous slide, these four examples they are given for that purpose only that they are liable to undergo some kind of fatigue and might be some accidents happen. So we need to take care of it. Fatigue fractures they occur without warning. Okay, they result in brittle fracture. About 80% of failure in engineering components take place due to fatigue failure. So this is very important. Fatigue fractures they don't give any warning. They result in brittle fracture. We have studied about ductile and brittle fracture in our previous lecture, consistent elongation just or uh, negligible no elongation. So you can say they occur without any warning. They just result in fracture. So about 80% of failure in engineering components will take place due to fatigue failure. So steels have generally a fatigue limit which is normally zero point 0.4 to zero point 0.5 times the tensile strength of the material. Steels have a good fatigue limit. I have told you about the fatigue limit and endurance limit in the first slide, which is normally zero point 0.4 to zero point 0.5 times tensile strength of the material. Which is so under uh, following conditions, the fatigue fracture progresses rapidly, like the maximum tensile stress of sufficiently high value, then large vibrations or fluctuations in applied stresses, then large number of cycles or applied stresses, then other variables which may change the conditions of failure such as stress concentration, overloading, corrosion, residual stiffness, etc. We all know that vibrations are unwanted in any mechanism, like in any machinery. Vibrations, if not required, they are unwanted. So automatically, after some time, some kind of large vibrations or fluctuations, see, they are not required. So they may lead to some kind of negative effect on the working of the machine. See, so somehow it is responsible for fatigue fracture. Then large number of cycles of applied stress, so continuously going for such cyclic stress, it may also lead to some kind of fatigue fracture. Then there are other variables also like overloading. Every machine has a, you can say, limit of working, and if you are overloading, then automatically you will understand that it may lead to failure, corrosion, unwanted thing. So it is better to use steps that prevent corrosion rather than going for corrosion because it is unwanted. Residual stresses also. So these conditions should be taken care of. And due to difficulty of recognizing fatigue conditions, fatigue failure comprises percentage of failure occurring in engineering. Okay. The point at which the curve flattens out is termed as the fatigue limit and is well below the normal yield stress. The fatigue strength is usually defined as the stress that produces failure in a given number of cycles. Usually, this is just a number given 107. It can be more than that. Okay, so you have to avoid stress concentrations, rough surfaces, and tensile residual stresses. Fatigue specimen must be carefully prepared. Right. For testing purposes also, it should be carefully prepared. Okay. Then fatigue properties of a material are affected by several factors. Now we will look out the several factors. The first one is corrosion. The effect of corrosion is to reduce the number of cycles required to reach for every stress amplitude. We can protect the steel against salt corrosion by simple using chromium or zinc plating. Do you understand that the effect of corrosion, okay, it is not required. So we can protect the steel against corrosion. This is just an example that steel is commonly used material. So we can protect it by using just chromium or zinc plating. So in this way you can avoid failure. Then surface finish, scratches, dents, identification marks can act as a stress razor. These can increase the stress and so reduce the fatigue properties. So it is important that short cleaning A surface producing surface compresses stresses and improves the fatigue performance. Electroplating produces tensile residual stresses and have a detrimental effect on the fatigue problem. Okay, so we can go with that also. Then temperature. As a consequence of oxidation or corrosion of a metal surface, increasing metal surface increase in temperature can lead to reduction in fatigue property. So we should take care of it also. That uh, corrosion of the metal surface increasing, so increase in temperature, you can increase the temperature, it can lead to decrease in the fatigue property. Say you should know the temperature also in that case regarding the material. So microstructure of an alloy. Alloy, you know that mixture of metal and non-metal to attain the required properties. Okay, you cannot use a pure metal, so you go for an alloy for getting proper properties at the application of the material for the material. Okay. Then composition of an alloy and its grain size can affect its fatigue property. In comparison to gross grain steel, finer grain steel, finer grain size steels have higher strength. I told you this earlier about that the composition of an alloy, okay, and its grain size, they really affect the fatigue property. So if you compare a coarse grain steel and a finer grain steel have higher strength. We have studied about these grain sizes and their effect on the steels earlier also. In addition to higher strength, finer grain size also results in better resistance to cracking. Okay, this if the grain size is fine, then it will give you strength plus it will give you resistance to cracking. It will give you better surface finish because you know that it will look better and it improves the plastic deformation. So fine grain size has its own benefit. In comparison to fine grains, coarse grain steels are less tough and have great tendency for distortion. So try to have the structure with fine grain size. Addition of lead and sulfur in steel increases its machinability and can act as nuclei for fatigue and so reduce fatigue property. We have I am repeating once again. Addition of lead and sulfur in steel. You understand? They are not, you can say, going with the green side. Here they are saying that if you are doing addition of lead and steel in lead and sulfur in steel, increases machinability and can act as a nuclei for fatigue and so reduce fatigue. Then we go for the residual stresses. Residual stresses are produced by fabrication and finishing processes. So we have to take care of them also. So case hardening of steels by carbohydrates results in compressive residual stresses on surface. It improves the fatigue. So several machining processes produces tensile residual stress which impair the performance. Okay, so we should take care of this residual stresses also, which are produced by fabrication and finishing processes. So heat treatment. See, this produces residual stresses within a metal by producing compressive residual stresses in surfaces. Case hardening improves fatigue properties. Case hardening is a kind of a heat treatment process. Okay. It is saying that by producing compressive residual stresses in surface, case hardening improves fatigue properties. So, however, tempering treatments reduce surface compressive stress and so adversely. Okay, so doing that. Then stress concentration. See, these are caused by sudden changes in the cross section, in the keyholes, in the holes, or sharp corners and can more easily lead to a fatigue. I repeat, in terms of stress concentrations, they say that they are caused by sudden changes. Okay, these are caused by sudden changes in cross section, keyway, holes, or sharp corners, and can cause more easily lead to fatigue failure. Even a small hole lowers fatigue limit by 30%. Can you imagine a small hole? So we have to take care before making any changes. Okay, before making any changes, we should take care at how we are doing it. As it is saying that even a small hole can lower the fatigue limit by 30%. So to study the effect of stress razors on fatigue, a specimen containing V notch or circular notch is prepared. We have done this in labs also. When specimen is loaded, the notch has the following effects: an axial state of stress is produced, the stress gradient is set up from the root of the notch to the corner of the specimen, and there is stress concentration at the notch. A crack is developed to the stress concentration at the okay, at the root only the crack is developed. Okay. Now fatigue fracture. This this results from the presence of fatigue cracks, usually initiated by cyclic stresses, surface imperfections, example, machine marking and slip stress. Okay. Now, although the initial stress concentration associated with these cracks, okay, are too low to cause brittle fracture. However, they may be sufficient to cause slow growth of cracks into the implant. Okay, the initial stress concentration with these cracks it may be low, but they are sufficient for slow propagation, slow growth of the cracks into the implant. And eventually, the cracks may become sufficiently deep, and therefore the stress concentration exceeds the fatigue strength, the fracture strength, and sudden failure occurs. You understand that the cracks they can also propagate or they can slowly grow and they can become sufficiently deep and therefore the stress concentration exceeds the fracture strength and sudden failure. Okay, so the crack propagation may take place and the stress concentration exceeds the fracture strength and failure occurs. It is reported that the extent of the crack propagation process depends on the brittleness of the material under test. In brittle materials, the crack grows to a critical size from which it propagates right through the structure rapidly. Whereas with ductile materials, the crack keeps growing until the area left cannot support the load, and on almost ductile fractures suddenly occur. Okay, we have discussed about this ductile metal materials earlier also. Then fatigue failure. One can recognize fatigue failure by the appearance of fractures. Fatigue failure has a number of specific features compared to failures with under static loads, like it occurs at a lower stresses than the failure at static load. Okay, with fatigue failure, they occur at lower stresses than the failure at static load, that is lower than the yield strength or ultimate strength. Now failure starts on the surface or near it. This failure starts on the surface or near it locally or in places of stress, strain concentration. Local stress concentrators are formed always by surface defects appearing on cycle loading or notches. Okay, there are local stress concentrators that are formed by surface defects appearing on cyclic loading. or notches as traces of surface treatment or the effect of surrounding. The failure occurs in a number of stages like accumulation of defects in the material, then nucleation of fatigue cracks, then you can go the gradual propagation and joining of some cracks into a single main crack. Okay, and then the rapid we have seen in the lab also that how the cracks they they come. Okay, then how the cracks travel and they join at the main crack and finally they rupture the final destruction. Okay, in the lab such kind of we've seen this while testing. Now this is a simple stress cycle for testing of fatigue. In the A, you can see that how this is a stress time diagram showing the reverse stress. Okay, the maximum and minimum value. Okay, and the B diagram is showing fluctuating stress. Okay, in terms of stress with stress and time. And the C diagram is showing irregular stress. You can see the three kind of stress: the reverse stress, the fluctuating stress, and the irregular stress with respect to stress and time. Okay, so here in the diagram, the cycles are shown for testing of fatigue. Now, failure has a very typical structure which reflects the sequence of fatigue processes. A failure usually has the initial zone of destruction, that is the zone of nucleation of microglia, the fatigue zone, and the final failure zone. The initial zone of failure is usually near the surface and has small size and smooth surface. The fatigue zone is the zone where a fatigue crack gradually develops. It has typical concentric ripple lines, which are an evidence of jump-wise propagation of fatigue crack. Okay, the fatigue zone is the zone where the fatigue crack gradually develops. Okay, it has a typical concentric ripple lines seen in the diagrams, which are an evidence of jump-wise propagation of fatigue cracks. The fatigue zone develops until the increasing stresses in the gradually diminishing actual section attain a level at which the initial, at which the instantaneous destruction takes place and forms a zone of final fracture. The main reasons for taking place of fatigue failure are: first is surface imperfections like machining marks and surface irregularities. The kind of surface imperfections like machining marks and surface irregularities. The second reason is stress concentrations like notches, keyways, screw threads, and matching undercuts. The third is uh, at low temperature, the fatigue strength is high and decreases gradually with rise in temperature. Okay. Then the fourth is fatigue strength reduced by corroding environments. Following surface treatments like polishing, coating, fiberizing method can affect their effect can be reduced with such kind of surface treatments. Okay. We have to take care of stress concentrations like notches, keyways, threads, machining and whatnot. Okay, we have to take care of that also. Then mechanism of fatigue failure. Now this is associated with the development and accumulation of microplastic deformations in the surface and is based on dislocation movement. The possibility of dislocation movement or stress below the yield limit is due to the random orientation of crystal in the metal structure. At rather low mean stresses, the stresses appearing in some crystals may be sufficient for movement of weakly locked dislocation. For this reason, Microplastic deformations and damage of thin surface layers can be observed in mild annealed metals already at an early stage of loading. Okay, the microscopic deformations manifest themselves in the form of slip lines in the surface, with the density of these lines increasing as the number of cycles also increases. Okay, in this way the mechanism is going off fatigue failure. As dislocation emerges to the surface, this dislocation is coming to the surface, the damage is enhanced and appears as steps. Slip lines become wider, change to slip bands, and gradually degenerate into extrusions and intrusions. An extrusion is a bulge, okay, an intrusion, a depression of slip bands called intrusion. Now, extrusion and intrusion, that is ridges and forms a rough relief of the surface. It forms a rough relief of the surface. Recesses are places of concentration of strain. These two terms, ridges and recesses, then recesses are places of concentration of strain and therefore of vacancies and dislocation. Understand how useful this recesses can. Understand that how useful this recesses can be. Then a high local density of vacancies and dislocation can result in the formation of voids and loose places where merge together, which are merged together to form sub-micro cracks. Okay, this high local density of vacancies and dislocation, they can result in formation of cracks and loose places which merge to form sub-micro cracks. The development and joining of sub-micro cracks in turn leads to formation of micro cracks. I repeat, you should understand this. The development and joining of sub-micro cracks in turn leads to formation of micro cracks. Now, fatigue are often referred to as progressive fracture, and fatigue is a result of accumulative process involving slip. High temperature increases the mobility of atoms, facilitating greater slip and deformation before fracture. The high temperature can give you deformation before. Highly localized stress is also developed at abrupt changes. Highly localized stress is also developed at abrupt changes in cross section, at the base of surface stretches, at the root of a tooth, at the edge of small inclusions of foreign systems, and at a minute blowhole or similar internal defects. Okay, these typical conditions will give rise to the susceptibility or to failure by fatigue. Okay, these typical conditions give rise to susceptibility to the failure by fatigue. Then the effects of alloying elements. See, alloying elements may give additional facilities or properties that may increase the fatigue limit or endurance limit. So we can go with that. A homogeneous mixture of two or more metals or a metal and a non-metal when fused together at a certain temperature forms a new metal after solidification. This termed as, I repeat once again, hope you understand, a homogeneous mixture of two or more metals or a metal and a non-metal. When fused together at a certain temperature forms a new metal after solidification, termed as an alloy. Metals in actual commercial use. See, alloy means formation of a new metal after solidification. Okay. Now, metals in actual commercial use are almost exclusively alloys and not pure metals, since it is possible for the designer to have an infinite variety of physical properties in the product by varying the metallic composition of the alloy. It is the demand of the industry that the material that is used by the design engineer to have infinite variety of physical properties in the product, and this can only be achieved by varying the metallic composition of the alloy. If you are going with it, then you are satisfying the physical properties required for the design engineer. Now, alloys are normally harder than the components. They are less ductile and may have lower conductivity, whereas a highly purified single crystal of a metal is soft, malleable, and with high electrical conductivity. And heat is once again a purely purified single crystal of a metal is very soft, malleable, and has high electrical conductivity. Okay. That is why pure metals are used only for specific application. The alloy is more corrosion resistant and is affected by atmospheric conditions. Okay. The conductivity of the alloy varies with the degree of the order of alloy, and the hardness varies with the particular heat treatment. The- What happens that the pure metals these are used only for specific application. The alloy that is used is usually more corrosion resistant, so it is better and is less affected by atmospheric conditions, so also it is better. The conductivity of the olefin alloy varies with degree of the alloy, degree of order of the alloy. The conductivity of an alloy degrees with the varies with the degree of order of the alloy, and the hardness varies with the particular heat treatment. Okay. So conductivity here is dependent upon degree of order of the alloy, and hardness is dependent upon heat treatment. Heat treatment is like quenching. So these gives hardness. Now alloys are classified as binary alloys composed of two components, ternary alloys composed of three components, and multi-component alloys. So most commercial alloys are multi-component. Okay. The composition of an alloy is described by giving the percentage either by weight or by atom. Okay, of each element in it. Okay, the composition of an alloy is described by giving the percentage either by weight or by atom of which element it is. Metal alloys, by virtue of composition, are often grouped into two classes. One is ferrous and one is non-ferrous. The ferrous alloys are those in which iron is the principal constituent, include steel and cast iron. And non-ferrous alloys are those alloys that are not iron based, like steel, cast iron. Alloys are widely used in industries because their physical and chemical properties can be easily varied to suit the exact individual requirements. These are artificially made. One can achieve this by preparing alloys of different materials. One can achieve this by preparing alloys of different metals. So here you can attain better properties in alloys. The following elements which are added to improve one or more of the following properties like tensile strength, hardness, toughness, corrosive and oxidation resistance, machinability, elasticity, hardening, creep strength, fatigue strength. You all know these all kinds of properties. The creep strength I will let you in the coming lecture. Okay. So alloy system. The improvement in the properties of an alloy system depends upon following factors. The first is manner in which the two or more metals are mixed with each other. Either they are melted and mixed, or they are agitated and mixed, or they are powdered and then mixed. It depends. Then the percentage of different alloying elements. See, this is important. We should know in which percentages you are mixing the alloy or why, because if by chance to some better properties, then you can say by the past experimentation you can attain such kind of different alloys with better properties. Okay, so percentage of different alloying metals or elements should be. Then temperature at which these are cooled. So these three factors are important, like the way they are mixed and the percentage of all the different elements, and at last the temperature. So it is possible that two or more metals which may be soluble in each other in liquid state, but may or may not be soluble in each other in solid state. In liquid state, they are liquid. It's possible that two or more metals may be soluble in each other. In liquid state, they are liquid, but in solid state, they are not. It is possible that they may retain their identity even if they are soluble in liquid state. Example, cadmium, bismuth are soluble in each other in liquid state, but insoluble in each other in the solid state. Okay, it is also possible that two or more metals which will be soluble in each other in liquid state with solid state. Example, copper and nickel. These are both soluble in the liquid as well as in the solid state. You cannot distinguish copper from nickel. So we should know these kind of, can say, things so that uh, easily you have the knowledge of alloy systems. Then solid solution. A solid solution forms when as the solute atoms are added to the host material. Crystal structure is maintained and no new structure are formed. In other words, you can say that when elements completely dissolve in each other in liquid, and so or the solid state, the resulting phase is called as solid solution. Okay, the elements dissolve each other in liquid or solid state, and then the resulting is called as solid solution. Solid solution form readily when solvent and solute atoms have similar size. Okay, uh, and electron structures. This is a line I will repeat. I'll tell you once again because uh, this is important. Solid solution form readily when solvent and solute atoms. I repeat once again because this you need to understand. The solid solutions they form when solvent and solute atoms are readily it is compositionally or chemically homogeneous, and the component atoms of the elements cannot be distinguished physically or separated mechanically. Only then they are easily mixed. Okay, they cannot be distinguished physically or separated. There is a homogeneous distribution of the constituents in a solid state. There is a homogeneous distribution of the constituents in the solid state so as to form a single phase solid solution. Then basically the solid solution are of two types. First one is the substitutional solid solution, and second is the interstitial solid solution. So we go with the first substitutional solid solution. When the two metals when the two metals in solid solution they form a single phase. They form a single phase centered cubic lattice. That is, in general, solute or impurity atoms replace or substitute for the host atom. It is called as substitutional solid solution. Okay. Then random substitutional solid solution or ordered substitutional solid solution. These are different kind of substitutional solid solution. And randomly they are or orderly they are. An interstitial solid solution, we can say that they can form, for instance, on melting together transitional metals and non-metals with a small atomic radius. The possibility for obtaining an interstitial solution is mainly determined by the size factor. That is, the size of the solute atom must be equal to or slightly smaller than the size of an interstitial void. You can see in the diagram, this is what one is the solid solution, and then it is going with the substitutional solid solution, and the last one is interstitial solid solution. These diagrams show that how carbon atoms are in between the iron atoms. Okay, one is solid solution equal, and then they are mixed. And the other is substitutional solid solution. Third one is interstitial solid solution. Alloy steels. An alloy steel may be defined as a steel to which elements other than carbon are added in sufficient amount to produce an improvement in the properties. Okay, steel in which elements other than carbon are added. Carbon is very important, but we are going with other than carbon. Okay, other than carbon are added in sufficient amount to produce an improvement in properties. The alloying is done for specific purposes to increase the wearing resistance, corrosion resistance, and to improve electrical magnetic properties, which cannot be obtained in plain carbon steels. So, the chief alloying elements which used in steel are nickel, chromium, molybdenum, cobalt, vanadium, manganese, silicon, tungsten. Each of these elements confer certain qualities upon the steel to which it is added. So, these elements they are separately discussed. What exact characteristics? This we will discuss in the next lecture for now because I have to take the MCQ also. So let me start with the MCQ. This is for some seconds and I'll start with the MCQ. Now the first question is like it is the failure of a material by fracture when subjected to a cyclic stress. So what do we call this? Either it is the fatigue, strength, with or corrosion. It is called as a fatigue. Okay. Then second, this occurs without any warning. They result in brittle fracture. This occurs. What I'm asking, this occurs without warning. They result in brittle fractures. About 80% of failures in engineering component takes this due to it. I have told you earlier also. This occurs without any warning. They result in brittle fracture. About 80% of failure in engineering components take place due to it. Fatigue fractures. We have discussed about this in the starting of the lecture. Okay. And steels have generally a fatigue limit which is normally 0.5, zero point 0.4 to zero point 0.5 times the tensile strength of the. You will say is statement is true or not. Read again and you will understand. Steels have generally a fatigue limit which is normally 0.4 to zero point 0.5 times the tensile strength of the material. True or false? True. So you have the answers in front of you. Just try to understand the question and then you answer. This dash is usually defined as the stress that produces failure in a given number of cycles. Usually, example one is fatigue stress. The effect of corrosion is to reduce the number of cycles required to reach for every stress entity. What is true or false? True. Then this results from the presence of fatigue cracks usually initiated by cyclic stress at surface imperfection, example machine marking and slip steps. What do you say? Fatigue fact initiated by cyclic stresses. So from that you can understand that okay, this kind of fracture may occur. Okay. In brittle materials, the crack grows to a critical size from which it propagates right through the structure rapidly, whereas with ductile materials, the crack keeps going until the area left cannot support the load, and an almost ductile fracture suddenly occurs. True or false? Understand the statement. Okay, it is true. Okay, understand it. We have discussed this in the lecture also. During the lecture, I told you the exact meaning of it. The dash is the zone where a fatigue crack gradually develops. It develops until the increasing stresses in the gradually diminishing actual section attain a level at which instantaneous destruction takes place and forms the zone of final failure. Fatigue zone. Highly purified single crystal of metal is very soft and malleable with high electric conductivity. True. Last question, the maximum stress. For this lecture, last question, okay? The maximum stress that a material can withstand without failure for a specific large number of cycles of stress is termed as fatigue or endurance. So we have studied about fatigue failure, this mechanism of fatigue failure for today, and I hope you might have understood the lecture. See, just understand what I have told you. Okay, if possible, read these books for reference. These- They contain knowledge which may give you uh, more knowledge, and think that um, thank you today for listening. Thank you very much.